center of mass, this axis of rotation. Okay. And so then in this case, we also then had these similar types of relationships between the movement of the center of mass and our angular quantities. And so here in particular, this told us that, right, the change in the displacement, right, of our center of mass, this ends up being r times our angular displacement, right, our velocity of our center of mass. This is r times our angular velocity. And then the acceleration for our center of mass, this is r times our angular acceleration. Okay. And with this, you had some problems, for example, like, if you had two objects, say, right, like let's say you had two wheels, for example, that they're both rotating together, right? And so again, I have that there's no slipping, right? And so if I wanted to compare, say, this omega large versus omega small, right? And so let's say, for instance, let's say this is r, and let's say this is, 3r, right? The key thing is that if there's no slipping going on here, what that means then, if I kind of zoom in here, right? If I look at a point on this side and I look at a point on this side, right? Both of these points, right? This is going this way, right? This one is going this way. So if they're not slipping against each other, what I know has to be true is I know that the tangential velocities and the tangential accelerations, these have to be the same, right? Because if they weren't the same, then that would imply that there's some degree of kind of slipping that's going on between the two. And so what I know here, because there's no slipping, what this tells me is that the tangential velocity and acceleration must be the same. Okay. So what that tells me here is, so I know then that my VL, right, this has to equal my V small, but I know this is going to be what? This is going to be 3r times omega L, and this is going to be just r times omega small. And so I can see that my omega L, this is just 1/3, say, omega small. Okay. Any questions on any of this? This is basically all the kinematic stuff. Okay. So this is pretty much what we talked about for rotational kinematics. When it came to rotational dynamics, we first mainly looked at so we didn't actually really look at dynamics too much. We focused more on kind of static cases. Well, let me cover that later. Okay. And so we said that the first thing was that, so just like we had these angular quantities that corresponded to different translational quantities, well, we had a similar thing here when we're dealing with rotational dynamics. So here what we had is we had this idea of torque, right, which we use this letter tau. Then this corresponded to basically force in the translational world. And then we had this thing that we called the rotational inertia, right, which was I. And this we said corresponded basically to the mass in the translational world. And so we had this Newton's second law, right? So over here where we said this net force is our mass times our acceleration, then the equivalent thing we had here is we had that torque is equal to I times our angular acceleration. Okay. And so we talked about this. Again, we didn't really get into problems that actually involved calculating things like angular acceleration given a torque, right? What we focused on was we focused more on static problems. And so, of course, the first thing we needed to figure out is how do you calculate torque, Right? And so the idea here, again, we said is that, let's say you've got something, and let's say I know that this is my axis of rotation. Then if I've got a force, for example, that is going, well, let's say in this direction, right? That the way we defined what the torque is we said that, okay, what we're going to do is we're going to take our force, right? And then we're going to look at what we call the line of action for the force. And we said that all the line of action was basically we're just going to take kind of, the direction that our force is going in, and we're going to extend it out infinitely in both directions. All right, so this is what we call the line of action. And then what we would do is we would look at this kind of closest distance that we have, right, from our axis of rotation to our line of action of our force. And then this thing here, which we use the notation R perpendicular, we said that this was the moment arm, or you could call this the lever arm of the force, right, with respect to the axis of rotation. Okay. And so then we said that, all right, so now what we're going to do is we're going to define the torque as it's just going to be whatever that moment arm is times whatever our force is. Okay. And then after this, we talked about, okay, well, this is definitely one way to calculate it. And this is really how we define torque, right? And so when people talk about like the lever arm for a force, this is what they mean, okay? In particular, they don't mean the distance from my axis of rotation to where I'm actually applying the force, okay? It's always, again, this distance from my axis of rotation to the line of action of my force. Now, we said that this was one way to calculate this, but again, this can be a little bit confusing for people. And so we said that another way to look at this is, well, if I now look at, say, this distance here, right? So if I call this R, then we can see that if we call this angle here theta, here, right? Then I can see what? I can see that this R perpendicular, this is just what? This is just R times theta, all right? And so what we can see is that, this R perpendicular, this is equal to R times sine of theta. And so what that meant is that we could also calculate this as R sine theta times F, right? But then another way to think about this is that I can imagine moving the sine over here, so I can think about this as R times F sine theta. And now if I think about what is F sine theta, well, so of course this angle here as well, right? This is also theta. And what I can think of as being F sine theta is basically this, right? So this is F sine theta, and this is what we called F perpendicular. Okay. So when I talk about the torque that's being exerted by a force relative to some axis of rotation, again, the definition of it is I look at the moment arm, which is the distance from the axis of rotation to the line of action, times the force. But then again, we can do a little bit of playing around. I can also think about it as being essentially the distance from the axis of rotation to where the force is being exerted, right, times the force times sine of theta. Or I can think about it as being the distance from the axis of rotation to where the force is being exerted times the perpendicular component of the force. In other words, the component of the force, again, that's perpendicular to this line here. All right. And so I could also think about this as RF perp guess I'll just remove this. Okay. And so again, these are all perfectly valid ways of calculating torque. We did say that, you do want to be careful, is you want to remember here, of course, that our theta, right here, this is the angle between the force and the line joining the axis of rotation and the point where the force is applied. Okay. So there was a question, is rotational dynamics going to be on our quiz as well? So again, we didn't deal with dynamics in the sense that what we looked at is, we looked at specifically the cases where our angular acceleration was equal to 0. Right, and so what we looked at was basically what we call cases of static equilibrium. Okay, and so in terms of the rotational dynamics that we're going to deal with, it's really rotational dynamics as applied to static scenarios, right? So this is cases like, I've got a, something like this, right? And then if I've got, say, let's say an object here, right, of mass 1, and I've got some object, say here, right, of mass 2, and then if I call this, say, the distance from here to here, if I call this R2, and I call this, say, R1, right, if this is my axis of rotation, and then we ask things like, what is the relationship between R1 and R2 if the board is in static equilibrium. Okay. And so the key thing we said here is that, okay, if you're in static equilibrium, what this told us, well, first of all, it told you that the net force, this has to be 0, right? Because if I'm in static equilibrium, nothing is moving, so there's certainly no acceleration, so I know that this is going to be true, right? But the other thing this told me that my net torque, this has to be 0 Newton meters because nothing is rotating either. Okay. And so then what that told me then is then this would allow me to do certain calculations. So for example, for this simple one, if I look at the torques that are being exerted, right? So there's a torque kind of going this way, right? There's a torque going this way. And so I can see this is just M2G. This is M1G. And so we can see that our net torque, right? If let's say we make again kind of the usual, we'll make this way positive. So counterclockwise, if we make this positive, then I can see that my net torque, well, so M1 is generating a torque, right, that wants to go clockwise relative to this axis of rotation. So I'm going to have minus the torque from 1 plus whatever the torque is from 2, and I know this has to be 0 Newton meters. Okay? And so this just tells me then that, okay, I know that these two torques, the magnitudes have to be the same. And so now if I look at the torque for 1, this is going to be what? This is going to be R1 times my force is M1G times sine of theta 1, which is basically this angle, right? And then I've got theta 2, so I know this has to equal R2 times M2G times sine of theta 2. And again, the nice thing with this type of problem is I know theta 1 equals theta 2. I know these are both not 0. That would be bad. These are both 90 degrees. And so I know that my sines are both just going to be 1. And so this just gives me R1 MG, R1 M1G equals R2 M2G. And so this tells me that R1 is equal to M2 divided by M1 times R2. Okay. So in terms of rotational dynamics, again, is the only thing that we really looked at were the cases for static equilibrium, where we said that, okay, we know that torque is equal to our rotational inertia times our angular acceleration. So if everything isn't static, in other words, nothing is rotating, I know my alpha is 0, so I know that my net torque, sorry, I should have net, I know that my net torque is also 0. Okay. So we had this problem, we also had, a bunch of problems that we dealt with that did kind of like this case, right? Where, for example, I've got some support cable here, and then, we would hang like some blocks below here. So let's say this is kind of M1, let's say the rod has mass, say, M2, or call it MR. And then, we could ask things like, all right, if I look at this as my axis of rotation, we could ask things like, what is the tension? In the support cable, right? And so for this 1, 2, 3, 4, 5, 6, 7. So for this one, again, if we look at, again, we talked about, right? So just like we had this free body diagrams for kind of regular dynamics, right? For our rotational dynamics, what we have is what we call, again, our force diagram. And so here, the only difference really is again, we go through the same routine, but what we're going to do now is we're not going to draw everything coming out of some one point, is we're going to kind of take whatever our picture is and draw all of our forces relative to this. So I know, for example, here, right, I expect there's going to be the force of gravity on the rod, right, which is mRg, kind of here. And then I know that, all right, there's going to be this force here, right, which is going to be the force of gravity due to this box. So this is going to be, say, M1g. And then I know I've got this force of tension kind of over here. And so we had these things, right? And so again, what we knew in this case is we knew that our net torque had to be 0, right? And so I guess just to make this a little easier, let's put some actual numbers here. So let's go ahead and say, M1 is, say, 2 kilograms. We'll say MR is 3 kilograms. We'll say that, say, this distance here, R1, let's call this, let's say 20 centimeters. This distance here, right, let's call this 35 centimeters, right? And then that would make this distance here, yeah, right, this is going to be, say, 50 centimeters. Okay. And so let's say our angle, let's just say it's, say, 30 degrees, right? And then again, what we know here is that, again, is we know that we have to be we're in static equilibrium, so we know that our net torque has to be 0, right? And so what I can do here is if I choose my axis of rotation to be here at this pin, sorry, I forgot. I should have also drawn the force from the pin. This one's a little bit tricky because of the way I've drawn this. It's not 100% clear. So I've got some force from the pin here, right? That's here. Okay, so sorry, my force diagram should have included this at the beginning, because again, I want to draw all the forces that are acting on this rod. So I said, is there gravity? Yes. What are we touching? Well, we're touching this block, we're touching this rope, but I forgot to include, right, we're also touching the pin here at this end, and so I've got a force from that as well. Okay. Now this one, again, this direction I drew, honestly, this one I drew kind of randomly because in this case, I don't have an easy way to tell exactly what this direction is going to be. So it could end up being that this thing is actually pointing down. We'll kind of see what happens when we work this out. Okay. So now I say I want to know the tension of the support cable. And so the key thing is here is, again, I don't know this FP and I don't know this tension, right? And so when I'm picking my axis of rotation, one of the key things that we talked about is that if we're in static equilibrium, right, then this says we're not rotating around any axis of rotation. Okay. In other words, anywhere I put my axis of rotation, whether I put it here, right, or if I put it, say, like over here, I don't want to draw it on here because that'll get a little confusing. I'll draw it and then I'll erase it, right? Or if I put it here, right, if I put it here, right, or I don't even have to put it on there. I could put it up here, I could put it down here, right? And as long as I'm consistent, right, with how I do all my calculations, I will always get the right answer. All right. And you can think about this. This is analogous to when we talked about in translational motion. We said that, okay, when you pick your coordinate system, it doesn't matter what you pick for kind of the orientation, what's positive, what's negative, right? As long as you use that coordinate system consistently, you'll always get the right answer, right? And we said the reason for that is, for example, like for a box sliding down an inclined plane, the box doesn't know what your coordinate system is, right? It's going to do the exact same thing no matter what you do. And so since there's kind of a real physical thing that's going on there, no matter what you pick your coordinate system as being, you know that it should give you the right answer, okay, as long as you use it consistently. Now, again, while it's true that then, again, I can use any of them, that doesn't mean that there aren't some that are easier than others, right? So like in this case, again, I could pick any of these, right, axes of rotation, but for in particular the case where I'm trying to figure out the tension in the support cable, putting my axis of rotation here at the pin, this makes my life the easiest. And the reason for that is by putting this axis of rotation here, this now means that the torque generated by the force from the pin at the axis of rotation, this is going to be zero, right? Because of the fact that since I'm right at the axis, my R is zero. So we know since our torque, again, is just RF sine theta, I know that this is going to do zero torque. And so that means now the only unknown I kind of have in my equation is just the torque from this tension. Okay? And so this was an important kind of thing, again, that we talked about to realize. Okay? So for this problem, again, I'm going to do then what I said here. So I'm going to pick this as my axis of rotation. And so again, what I know is that I know that my net torque, again, I know this has to be 0 Newton meters. Let's again go ahead and we'll just stick to kind of the mathematical convention where we'll say going clockwise around the axis of, counterclockwise around the axis of rotation is positive. And then I can see what? So I can see this tension. This is going to be a positive torque. Both of these forces of gravity, these are going to be negative torques. And so I can see that I have, say, we'll call this R tension, right, times the force of tension times sine of theta, right, minus, and then I'm going to have, say, R of the rod, right, times FRG times sine of theta of the rod minus R of the box times the force of gravity on the box, right? And I know, again, this has to be zero. And here again, I know that very conveniently, theta R, theta B, I know these are 90 degrees. Okay. And so I can basically then just solve this for my T, right? So again, this is just going to be 1, this is going to be 1. So I can move my those terms to the other side. So I've got this RT times T sine theta. This is going to be RR MRG, right, plus RB MBG. And so this tells me my tension here, it's just whatever this is, right, divided by RT sine theta. Okay. And so now we just plug in our values. So I've got 0.2 meters times oh, sorry, I shouldn't, I call this MB, I call this M1. So let me be consistent here. R1, M1, R1, M1. So this should be R, 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 O. Okay. So I've got this 0.2 times 2 kilograms times 9.8 meters per second squared plus, oh, sorry, this is my, for my rod, I've got 0.35 meters, right, times 3 kilograms times 9.8 meters per second squared. All right, adding this, and then I'm dividing this all by 0.50 meters times sine of 30 degrees. Okay. And then just very quickly getting my number here. I get that this is about 56.8 newtons. Okay. All right. Questions on this part? Okay. Separately, actually, I did realize, so we do actually know that this has to be going up, right? And the reason I know that this has to be going up is that if you imagine, right, so I said again, if we're in static equilibrium, I can pick my axis of rotation wherever I want. So, for example, if I want to know the direction of the force from the pin, if I imagine I put my axis of rotation here where the tension is, right, again, I know my net torque has to be 0. So if this were my axis of rotation instead, right, again, I know that this is not generating a torque. I can see that these two things generate what? They both generate counterclockwise torques around this axis of rotation. That means this has to go generate a clockwise torque in order to offset these. So I know that actually this has to be going up and to the right. Okay. Questions on this one, and then we did problems where you would then actually calculate what is the force at the pin. In this case, now that I know what the tension is, right, I can calculate the force on the pin, right, and so I can use, for example, the fact that my net force is 0 newtons, right, to find my force from the pin. Okay. Questions on this? The other type of problem we had with this was like this one, right, where you had a couple of ropes. Right, and then you had a person, say, somewhere. And then we talked about, okay, depending upon where the person is, what are the tensions in the different ropes, all right? Unless somebody asks, I won't go through this again. If you go back and look at one of the worksheets, I think this was on the first static equilibrium worksheet. If you look at it, there's several problems like this. And so again, you could figure out, we did things like either given, the mass of the board and the person and where they're standing, we calculated what were the tensions in the two ropes. We did things where it's like, okay, if I tell you what the tensions are, can you tell me where the person is standing, right? And all those various different iterations. Okay. Questions on this? So again, in rotational dynamics, really what we limit ourselves to, again, were these static situations where we knew that since our net torque is equal to our rotational inertia times our angular acceleration, and we know that if we're in static equilibrium, there is no angular acceleration, so we knew that our net torque always had to be 0. Okay? All right, so then the next thing that we talked about was this idea of rotational kinetic energy. Okay. And what we said here, again, is that we know that kind of in the translational world, right, we know that this was equal to 1/2 mv squared. And then we said that again, the parallels keep on continuing here. So we know that for mass, we said that was the equivalent thing in the rotational world is rotational inertia. And for instead of speed, it's going to be our angular speed squared. Okay. So we talked about this idea of rotational kinetic energy. And where we really kind of used this was, basically this type of problem, right? Or if I had something like this. Okay. And so we said, if the disk rolls without slipping, what is its speed at the bottom? Okay. And so, we would look at essentially, whatever this initial height is, right? Here again, we had some angle theta. And so the key thing that we said here is that if you're rolling without slipping, I guess I should have mentioned this before. So one thing we said is that to start rolling without slipping, right? Kind of. Then you had to have friction, right? Must have friction. And in particular, since we said if we're rolling without slipping, we know that in fact it has to be static friction. Okay. So we know that we have static friction, right? And so if I were to draw my force diagram for this thing, right? Again, I've got my force of gravity. Right? I've got my normal force. And then what I'm going to have is I'm going to have a force of right, static friction. Now this thing is not very perpendicular. It should be more like this. Okay. So this is what our force diagram looks like. And so the key thing we said is that if you're rolling without slipping, it's still the case that only gravity, I shouldn't say this, let me change it, let me say it. With rolling without slipping, we know that the force of static friction does no work. Okay, and so again, we talked about this, one way to think about it is that if we think about this in terms of work being a transfer of energy, well, the force of static friction is coming from the incline in this case. Can the incline impart any energy into the disk? Well, no, not really, right? Or the other option was that if we just think about, the force of static friction is being exerted at this point here, this point of contact, and we said that the speed of the point of contact, for that portion of the wheel that's in contact with the ground, that's always 0. Okay. And so because of that, what this told me in this case is this tells me that, again, only gravity is doing work. And so this again told me that my mechanical energy is conserved. And so this point, again, is just our usual. We know that our EF equals our EI. And so I've got what? I've got my UGF, right? And the key thing here, so now I'm going to have rotational kinetic energy, plus I'm going to have translational kinetic energy, right? And then I've got this same thing here, UGI plus K rho I plus KTR. All right. And so if we do kind of our, oh, sorry, I forgot you guys use this notation. So if I know here, if I set this PEG equals 0 here, all right, then what I've got here is I've got 0 joules plus 1/2 I omega F squared plus 1/2 M VF squared. This equals MGH plus 0 plus 0. All right. So now again, initially when we look at this, we're like, oh, well, crap, like I don't know VF, I don't know omega F, right? So I've got two things that I don't know here. But what we said is that it turns out that, when we look at this equation for I, so again, we don't expect you guys to calculate this, but for example, if I tell you that this just rolls without slipping, if I tell you that I, for example, is 1/2 mr squared, right? Then what I can do is I can rewrite this as this is going to be 1/2. So I've got mr squared, that's my I. And the key thing here is that we know that since we're rolling without slipping, we know that omega F is just V over R. Okay. And this goes back, way back up here where we talked about this relationship between rolling without slipping and then our center of mass velocity and things like that. Okay. And so this is going to be then V over R. And then I've got plus 1/2, oh, sorry, I forgot a 1/2 here. All right, plus 1/2 MVF squared. This has to be MGH. And so if I do this, my R's, these all cancel out. I've got a squared here. And so what I end up on this side is I end up with this 3/4 MVF squared. This has to be MGH. And so this tells me my VF. This is 4/3 GH square root. Okay. And so again, so for an object that has both translational motion and rotational motion, so whether it's something like this where it's rolling without slipping, or even in a case like, let's say I've got something like this, right, where I start this thing up here, right, and then it's going to go to here, and then it's going to start flying through the air, right? As this thing is flying through the air, again, it's got both translational motion as well as rotational motion. And so when I'm looking at this object, even as it goes up here, again, I'm expecting to have both rotational kinetic energy as well as translational kinetic energy, right? If you have something, again, where it's kind of fixed, right, and then it's just moving around like this, right, where I just have something like this, then of course here there's no translational kinetic energy because it's only rotating, and so I just look at this in terms of the rotational kinetic energy. Okay. Questions on any of this? Okay. And then we talked about angular momentum, right? And then again, our parallels continued, right? We said regular momentum, right? We know that this was P is equal to mv. And so we said that, okay, then for angular momentum, we expect this to work similarly. And so again, we know that for the letter we use for angular momentum happens to be the capital L. And then again, this is going to be I, and this is going to be omega. Okay, because again, our mass is the same as our rotational inertia, and our V is the same as our angular speed, or I should say not the same. These are the analogous quantities. All right. And really the key thing that we talked about for angular momentum here is that we said that, okay, so it turns out that if I look at net torque, this is equal to I alpha, but another way to look at this is change in angular momentum over change in time. Okay. And then what this told us then is that the change in angular momentum, this is our net torque times our time. And so what this tells us then is if there is no net torque, then we know that angular momentum is conserved. Okay. And so again, this is exactly analogous to what we had in the translational world, right? Where there we have that, our F net, and this is MA, right? But I could also think about this as being dP dt, and then this said that, okay, then my change in momentum, this is just my net force times delta T. And so this said again, if no net force, then regular momentum is conserved. Okay. Now, in the translational world, when we studied conservation momentum, what we really looked at is we focused on collisions, right? And the reason for that is in the translational world, if I only have a single object, right, and I don't have any net force on it, then this really is pretty boring, right? There's really nothing that's going on here. It's just going to move. Whatever its velocity is, it's not going to change. And so, nothing really fun there, right? But we said that the thing that makes angular momentum more interesting is that unlike in the case for translational momentum, where again, we were always assuming that our mass is fixed, the thing is that for angular momentum, this rotational inertia I, even for a single object, this can change, okay? And so here's where we spent more time talking about this rotational inertia, right? And so again, we said that it's called inertia because again, just like in the translational world, what inertia told us is how hard is it to change the thing's velocity. Rotational inertia is the same thing. So it's telling you for this object, how hard is it to change its angular velocity, right? And so the key thing here is we said that this depends on the mass and, right, how the mass is distributed, right? And in particular, we said that the farther the mass is from the axis of rotation,
like we explained in our mini survey, every day we engage
the greater
in small acts.
the rotational inertia. And so, we talked about some, simple cases where, like if I've got, let's say, something like this, right, where this is my axis of rotation, and I compare that to, say, something like this, right, where this is my axis of rotation. If this is M and this is M, then I know that this one on the right, this has more rotational inertia, right, than this one, because again, I've got the same amount of mass, but this is, in this case, twice as far away from here, so I know this has more rotational inertia than this. All right, and so we did lots of different examples of, scenarios in terms of figuring out what's the rotational inertia. Some of the ones that are kind of more, that came up a bit is, so for example, we also talked about, if you've got, say, a hoop, right, versus, say, say a solid disc, right? So if we assume that M and R are the same, then what this told us is that the rotational inertia of the hoop, we knew this had to be more than the rotational inertia of the disc, right? Because again, in this case, I should say it again, and this is all relative to center of mass. Okay. that this has more rotational inertia than this because of the fact that, again, here, all of my mass is this distance r away. Here, I've got the same total mass, but some of the mass is, again, going to be right next to the axis of rotation. So that told me then that my rotational inertia here is going to be less than here. Okay. One thing to also point out, and I'll try to make sure that I'm consistent about this or careful about this, is when you talk about things like rotational inertia, angular acceleration, torque, all of those quantities, all of our rotational motion quantities, all of those things are always calculated relative to your axis of rotation. Okay. So you need to make sure that you're specifying, where are you taking your axis of rotation to be, right? Now, a lot of times it's kind of, clear where you should pick it. So for example, like this case, it makes sense. Pick this as your axis of rotation because we know that is actually what we're going to rotate around. But, when we had cases like this, we said, okay, maybe you want to put your axis of rotation here on the left side. Maybe you want to put it on the right side. Maybe you want to put it where the person is, right? All of these possibilities, again, were possible. And the key thing is anytime I was calculating the torque, right, or I guess in this case, really just the torque, again, I needed to know where my axis of rotation was so that I could calculate the torque appropriately. Because again, all of my rotational quantities, they're all relative to some axis of rotation. Okay. So we had this, we also had things like, a hollow sphere, right? I think we did solid sphere, right? Etc. And for these two, we said that kind of the easier way to look at these two was, instead of looking at it kind of from the top down, if we looked at it kind of this way.
일단 이걸 좀 제끼고 이동을 좀 해주면 좋아.
Right? We said that, okay, when I'm looking at, again, how my mass is distributed, again, I don't care about, the vertical difference in how the mass is, right? So if I have something that's like, this, where this is my axis of rotation, right? Then that's going to be exactly the same as if I had something that looks like this, because again, it doesn't matter that, again, this thing kind of moves down here, right, versus this one. What matters only is how far am I from the axis of rotation itself. And so we said, so if we look at this, again, if I imagine kind of squashing this thing, right, so that it's flat as a pancake, I can see that more of the mass is going to tend to be on the outside than in the inside, versus for a solid sphere, again, more of my mass is going to be towards the middle than it is towards the outside. And so if I were to compare the rotational inertia of this and this, I expect this to be more. But even when I compare these then to a solid disk, again, for the solid disk, I expect all of my mass is kind of equally spread out right here relative to this axis of rotation, evenly spread out. So here again, I've got more stuff towards the edges than in the middle, right? So in other words, more of my mass is concentrated away from my center of mass, right? So if that's my axis of rotation, I expect my hollow sphere should have more rotational inertia than the disk, and my solid sphere should have less, because here now, instead of being evenly distributed, most of my mass is more towards the center. Okay. So we talked about this, and then, we talked about kind of the typical examples are, like figure skater pulling in their arms. Right. And so by pulling in their arms, again, this reduces their angular momentum, their rotational inertia. And so if they were spinning, right, then by pulling their arms in, because there's no net external torque acting on them, then we know that their angular velocity has to increase because their rotational inertia, their angular momentum has to be conserved. Okay. So there's no net external torque.
아니 차라리 그거를 이제
This tells me
다른
my
거
angular
있었어요.
momentum.
근데
It's not
일단은 내용도 있는데 괜찮으니까 그 효과음을 듣고
So if I
내가
reduce
이제
this,
네가 내가
then
너한테 보낸
this
걸
means
알겠지만
that
약간
my
한
angular
번에 보면
velocity
마지막에 그 기사 앵커 그 사람
must
말고
increase.
느낌을 약간 뭐라고
Any questions on angular momentum, or would people like me to work out some other problems relative to either, I guess, well, honestly, anything, angular momentum, or the rotational dynamic stuff, or the rotational kinetic energy? Okay, if not, then the next thing that we talked about after all of this stuff then is when we started getting into simple harmonic motion. Okay. And so in particular here, again, we only looked at two things. We looked at the spring block system, right? And we looked at the simple pendulum.
그 앞에 보통 아저씨가 낮은 Y 하는 그 부분 있잖아요.
Yeah. And so the key thing, we said that for simple harmonic motion, in order for an object to exhibit simple harmonic motion, we had to have what we called, again, a linear restoring force.
그 웨지 대시다가 꺼져. 그리고 한 1, 2초 정도 흐른 다음에 낮은 Y 하고 이제 what is more in disengage 있다고 말하는 거지. 이렇게 하고 그리고 일단 이 부분 좀 줄일까? 좀 줄일 부분 줄이자.
And so again, we said here,
10분 넘지는 않을 것 같은데.
So what this meant again is restoring.
짧게 하는 게 좋지 않을까?
This means force is always opposite the displacement. So in other words, it's always pointing towards the equilibrium point. And then linear says that is force is directly proportional to the displacement.
왜?
In other words, if we double the displacement, 2x displacement, this means 2x the force. All right. And so then with this, again, the main things we talked about were the spring block and the simple pendulum. So for the spring block system, we talked about our spring force. This is basically minus kx, where here k is the spring constant. And again, this is something that we had talked about way back when we did work and energy, right? So this basically tells us like how stiff or strong. Right. X, this is our displacement. From equilibrium. So for a horizontal case, for horizontal, this is just just kind of how much the spring is stretched or compressed.
그러니까 that's a justification.
And so, we did some problems, just to get used to how these things work. So if let's say we had something here where this is my, say, relaxed length, say L0, and now let's say I put this here. So I attach a mass here, and now let's say kind of this distance here is say x0. Then we said that, all right, well, if we look at our free body diagram, we've got Fg down, we've got Fs up. So if I consider this direction to be positive, then again, if I know that we're in equilibrium, all right, we'll say 0 meters per second squared, since assuming nothing moves.
이것도 지금 약간 justification.
And this told us that our
약간
Fs
왜냐면
minus Fg equals 0. So this told us Kx0, this had to be equal to Mg. And so we said using this, like if I tell you, what's, for example, the relaxed length and how much it's stretched, and I tell you the mass, then you can figure out what our K is going to be, or, typical kinds of things. And so one of the key things we said was that for a spring block system, that if we look at the period, right, this was 2 pi root m over k. And again, for all of these, we said again, period is time to one full oscillation. Right, and we said like frequency. This just is 1 over t. This is number of oscillations per unit time. And then we also talked very briefly about this idea of angular frequency, omega, and this just ended up actually being 2 pi times f. So we talked about this, we talked about the period, we said that the other things that are interesting are the amplitude, and this is just the maximum displacement from equilibrium. And so we said that, if you looked at this, simple harmonic motion was basically sinusoidal. And so if we assume, right, so if we assume we're at max displacement at time t equals 0 seconds, then our x of t, this is just our amplitude times cosine. And then again, you can do this 2 pi capital T t, or again, using the other ones, I can do this as 2 pi ft, or this is a times cosine length t. And so if I'm looking at, say, graph like this, so this is x and this is t, then we said that, essentially what we get is something that looks like this, right, where this is going to be my amplitude, this is minus the amplitude, and then of course this time here, this is the period, right, and then of course this thing would continue doing this. And so we said this is what our position versus time looks like. And then we said from this we could actually figure out things like our velocity versus time. Is that then we know that our velocity versus time, again, I know that on a position versus time graph, I know that my velocity is just the slope of the tangent line. So I can see here, that I start off at 0 and then I go to a negative slope, right? I hit my maximum negative value here and then I go back to 0 and then so on. And so if I look at what this is doing, right, what I would expect then is I expect to start at 0, I expect to go to some negative maximum value, then I come back up here, and then I go to some positive maximum value, and then I come back here, and then it goes like this. Right? And so now what this is going to be is this is going to be my Vmax. Right? And this is going to be minus Vmax. And so this is going to be minus Vmax times sine of, say, 2 pi t over t. Again, and you have, the other ways to write the argument to the sine. And then last but not least, we talked about what the acceleration looks like. And we said that, for acceleration, again, it's a similar kind of thing. We know that on a velocity versus time graph, the acceleration is the slope, so I can see what here. So here I start off some negative value, then I go to 0, then I go to a positive, and I go up to 0, back down to 0, and so on. So I expect this to look something like this. Right? Or this is now my maximum acceleration. Right? And the key thing is I know, of course, that the periods for all of these things have to be the same. Right? And so what I get here is I then get that my A of t, this is going to be minus A max times cosine, say 2 pi f t. Right? And then we came up with some relationships between some of these things because, again, we knew that for our spring block system, we knew that mechanical energy is conserved.
scientific evidence that 보여주는 말이 계속 반복을 하면 그럼 뇌가 그렇게 생각을 한다는 거잖아? 그러면
And so what that told us then was that our E total, right, this had to be whatever our elastic potential energy is plus our kinetic energy. And so that meant that, we know that when we're kind of at the greatest displacement, right, so this is at max displacement, right, which is basically x equals a, we know then that our total, this is just going to be all our elastic potential energy, which is going to be 1/2 Ka squared, and at the equilibrium point, right, or basically x equals 0, then our total, this is going to be, it's going to be all in kinetic energy, and so this is going to be 1/2 m Vmax squared. And then we could use these things together to basically tell us, okay, then this tells us then that 1/2 Ka squared, this has to be 1/2 m Vmax squared. And so this gave me a relationship. So I could write, my acceleration as being the square root of m over k Vmax, right? Or of course I could do it the other way. I can say my Vmax is the square root of k over m times a. Right? So that if I have one of these two things and I know the mass of my block and my spring constant, I can get the other. And then the other thing that we said that we knew is we knew that since we have this linear restoring force, right, so if I look at the magnitude, it looks like this. And so we know that the max force, again, this occurs at maximum displacement. And so this tells me then that my Fs max, this is just going to be Ka, but this is just what? This is just m times A max equals Ka, so this tells me that A max is K over M. Okay. And so again, we had like a bunch of problems besides just calculating what's the period, right? And how, if I want to change the period, what can I do in terms of changing, either the mass of my block or my spring constant, right? That will result in different changes in my period for my system. We talked about also then just using kind of conservation of mechanical energy to figure out things like, what is our speed or our, displacement, right? At certain points. So for example, I gave the speed as a function of the position. You can also, since we have these equations, right, for the position, velocity, and acceleration as functions of time, you can also, of course, use these to calculate, where we are or what our speed is and all that as functions of time. One thing to be careful of for these is that the arguments must be in radians. So this is the one place where you have to use radians, okay? Is that when you're looking at the position as a function of time, if I ask you, what is the position at time t equals 2 seconds? When you do this cosine of 2 pi t times 2 seconds, this has to be in radians. Your calculator must be in radians to calculate what's the position. Okay? And questions on any of this? Otherwise, the last thing we then talked about was the simple pendulum. And the main thing we said here was that this only approximates harmonic motion, right? And when theta max is small, right? So here we said theta max is, basically something like, less than maybe about 15 degrees or so. Okay. But when you do have a small maximum theta, then we could say that this thing basically looked like simple harmonic motion. And so then we said that for a pendulum, this period ended up being the square root of L over G, where L was the length of our pendulum, G is the acceleration due to gravity. And so, we said in particular, this does not depend upon the mass of our bomb. For both of them, right, neither of them depend upon the amplitude of your oscillations, right? For a simple pendulum, again, of course, doesn't depend as long as your maximum is still less than 15 degrees. Right, so for the spring block system, it only depends upon your mass and your spring constant. It doesn't matter if you're going horizontal, vertical, at some weird angle, if you're in outer space, if you're on Earth, whatever your mass is and your spring constant, that completely determines what's your period for a spring block system. Similar for this simple pendulum. In this case, it doesn't depend upon the mass at all. It doesn't depend upon, again, what my amplitude is. Again, as long as my maximum amplitude is small enough. It only depends upon the length of my pendulum and the force of the acceleration due to gravity, or like we saw in those cases where we put our pendulum in an elevator, whatever our kind of effective acceleration due to gravity was. All right. In terms of, after that, again, the equations for things are all the same. Our basic, graphs also for our, position, velocity and acceleration versus time. Again, it's going to look exactly the same here. The only real difference is how you actually go about calculating the period. Okay. And so then, of course, again, like with this case, we could use the fact that total mechanical energy is conserved. Right. And so in this case, our E total, this is going to be whatever our gravitational potential is, plus K. And so this told us at kind of max displacement. And our E total equals our maximum gravitational potential. which is
그러니까 근데
mgh
뭐야
max,
일시적시
and then at equilibrium, right, or basically x is equal to 0. We know then that our total here is equal to k max. This is just 1/2 m
오케이.
max.
첫 번째 건 좀 애매하지 약간.
Okay. And so then again, we, use this conservation of mechanical energy
그러니까.
to, calculate what the speed was when we were at a particular angle, or calculate the angle when we're at a particular speed, and so on. So kind of like that very first problem that we started off the review session with. Okay. All right, so this is basically everything, all the topics that, may show up on the quiz and the test. Are there any areas that people want me to review again, or want me to do some extra problems with, or anything like that? PEG max is equal to kinetic energy. Yeah, right. So again, so for this scenario, for the simple pendulum, again, we know that mechanical energy is conserved, so we know that again. Whatever our energy is, it's always equal to whatever's our gravitational potential plus our kinetic. So that means when I'm at the maximum displacement, right, I'm at the maximum displacement, I know that my V is equal to 0, right? So that means I don't have any kinetic energy, so all I have is gravitational potential, and so I know that has to equal my total mechanical energy. Conversely, when I'm here, when I'm at x equals 0, right, so this in particular tells me that my h is equal to 0 meters, right? That means that I don't have any gravitational potential energy, so all of my energy is in kinetic, and so that also will equal E total. And so, yeah, like you said, so that means that this PEG max, this equals K max, right? Just like how for the spring, PEEL max, this is also equal to K max. Okay. Other questions? Okay, if not, then we'll go ahead and call this the end of the review session. However, if you have questions, at any time before class tomorrow, as always, feel free to shoot me a Zoom or an email. Again, I'll try my best to be keeping track of things so that I can answer in a timely manner.